Welcome back. I think we are ready to resume. So that is the 2024 Mary Cartwright Lectures by Professor Bethany Marsh. The event was opened by Francesca Fedele, Dr. Francesca Fedele. Both Bethany and Francesca are at the University of Leeds. And after the accompanying lecture, we are now ready to go into the Mary Cartwright Lecture. And I guess, Bethany, you are invited to share your screen. Thank you. So we continue. So presentations of reflection groups. That is the second part. Bethany, the floor is yours. Thank you.
Okay, thank you very much. It's a delight to be here. Thank you very much for the opportunity to speak, and thank you for that beautiful talk, Francesca. So that was perfect. So look forward to saying some more about our joint work. So essentially, I'm going to talk about the case of complex reflections. So we've seen that reflections can be defined for real spaces, for Euclidean spaces, and there is a similar definition for a complex space, a complex vector space. So let's go into that. So I'll start by talking about what are these complex reflection groups. So they're sometimes called unitary reflection groups, particularly in the older work. It's more common to say complex these days. So we need to say what is a reflection to start with. So we're going to take a complex vector space of dimension n, c to the n, and then a reflection on V is, so it's a linear map. So an element S of the general linear group on V. So this is the group of invertible linear maps from V to V. And what it must do is, as before, it must fix a hyperplane pointwise. So we'll call the hyperplane HS, as in Francesca's talk. So it fixes a hyperplane HS pointwise. And in this more general context, we ask for it to have finite order. So in other words, S to the R is the identity for some R in M. And I guess we should also say S is not the identity itself, so we don't count the identity as a reflection. Okay, so it's a very similar definition. And you can see if we were in the real case, the order would have to be 2. So a complex reflection group is then defined in the same way. So it's a subgroup of GLV generated by reflections. So all possible products of reflection. So as Francesca mentioned, I mean, the actual elements of the group needn't be reflections themselves. They could even be rotations in the Euclidean case. So the same kind of thing is happening here. And if we had a reflection group, we can regard it as a complex reflection group by complexifying it, as Francesca mentioned. So I mean, if you think about it in terms of matrices, you just take the same matrices, but regard them as complex matrices. That's basically what's happening. And you could do that more algebraically if you want, by tensoring with the complex numbers. So instead of working with the Euclidean space r to the n, you would work with C tensor r to the n, which would be isomorphic to C to the n. Okay, so I'm going to focus on an example, which is the group we've been looking at. So we'll take positive integers d and n, and we take a primitive d root of unity in the complex numbers. So omega to the d is 1, and all the other roots of unity are powers of omega. So then we can define a group which is given the notation GDDN. And of course, we can think of linear maps as invertible matrices. So that's what we'll do here. So it's the set of complex n by n matrices of a certain kind. So each entry is either 0 or some power of omega. So 0 or a d root of unity. And every row and column has a unique non-zero entry. And then the product of these non-zero entries is 1. So you can see this is a generalization of what Francesca was talking about, because if we took D to be 1, the non-zero entries must all be 1. And then we just get what's usually called a permutation matrix. So it's just, you take the identity matrix and then you just permute the rows and columns. So this is actually just isomorphic to the symmetric group. Of degree n, which Francesca called WAN minus 1. So that's its Coxeter diagram. So it's n minus 1 because we had n minus 1 transpositions generating it. So 1, 2, 2, 3 up to n minus 1 n. So you always have this discrepancy. And if we take G2 to n, as premised, type dn is appearing here. So this is actually W of dn. It's actually now the same n. And this is permutation matrices where the entries are plus or minus 1. And so it's the same kind of idea, but it's signed permutations, they might be called. With an even number of sign changes. So the product of those entries must be 1. In fact, you could consider, you don't have to have this third condition, you would still get a complex reflection group. But I'm trying to just focus on one case here. But if you did that, you get Bn would come out as a special case. So that's also an important one. This is actually a subgroup of that one. Okay, and it's nice to focus on the irreducible case where there are no invariant subspaces apart from 0 or the whole space. So a complex reflection group is irreducible if the only invariant subspaces of V are the 0 subspace and V itself. Okay, we can somehow reduce the study to these cases. And as in the real case, there's a lot of interest in classifying these kind of situations. So, and in fact, that has been done. So it's done by Shephard and Todd in 1954. So if we have a finite, so the finite ones have been classified. So a finite irreducible complex reflection group. Then what can be GB? It could be, there's an infinite family with 3 parameters, 3 positive integer parameters. And the case E equals 1 is the one we're focusing on here. But let's mention in passing, if you have GD1n, it's the same as GDDN, but with that last restriction removed. And the others have a similar definition, but they are different groups, non-asomorphic. Okay, and then there are 34 exceptional cases. Okay, so let's try to analyze. So yes, the question we're looking at is how can we present these groups? So let's take G to be one of these groups. And we might focus on presentations where the generators are reflections, because it's generated by reflections. So that's very reasonable. So let's take sigma to be a set of reflections in G. So these are these elements which fix a hyperplane pointwise and have finite order and are non-trivial. Okay, yes, sorry, I meant to say, yes, we can ask about presentations of these groups, but actually I'm going to be focusing more on the braid group. Yes, I should have remembered that. Okay, so here, so what is the braid group? What is the braid group of this group? So as Francesca mentioned, we can take the vector space V and remove the hyperplanes. And that is a smooth manifold. Okay, and so there's some technical aspects here. So the group G acts smoothly. I mean, it's a very nice group. It's just acting by linear transformations on V. So it's freely. Now that means that nothing has a fixed point. No element has a fixed point apart from the identity. And that's because we've actually removed all the fixed points, which are the hyperplanes. And there's another technical condition that it acts properly. And that's essentially because it's finite. So it's, that means we can form a quotient manifold whose elements will be the G orbits on V. So take a point V and then look at all of its images under the group. That would be an orbit with V naught by G. That's also smooth, nice smooth manifold. And then the braid group of G is the fundamental group of this manifold. So we choose some base and then we look at loops starting at that base point. And then the operation in the group is given by composition. We have to look at loops up to an equivalence, but that's basically the idea. So it's measuring topology of the group in a certain, of the manifold in a certain sense. Okay, so this is quite a technical definition, and one wants some nice pictures of braids like Francesca was talking about in this case as well. So Francesca was talking about B W delta, and she denoted that as A delta. So this was the braid group associated Coxeter diagram. So a special case would be the real reflection groups, giving the braid group she was talking about. So how can we do this? So let's focus on GDDM. So we take a disk D, and then we can take the cyclic group CD, okay, so a cyclic group with D elements. So it's just isomorphic to Z mod D, the integers modulo D, if you want a more explicit version of it. So it just contains one element of order D. And this acts on D by rotation. So the generator just moves it by a dth of a revolution. So if CD is generated by G, then G rotates by 2 pi over D, anticlockwise. So if you do that D times, you get back to the identity. And then what we can do is form an orbifold. So these are quite remarkable generalizations of manifolds. I think Thurston introduced them, or at least was the prime in introducing them. So we'll call that OD, and this is D modulo CD. So what this actually does is it behaves just pretty much like the disk. But as Francesca said, there's a point at the origin which is actually fixed by CD. Every other point is in an orbit of size D. And if you apply the group to it, you get D points. But the point in the middle is fixed by those rotations. And it has different properties in the actual orbifold. So if you remove the origin, that path there would not be possible to a trivial path. If the origin was just a normal point in there, you could just collapse it down. And in the orbifold, it's something in between. So if you go d times around that point, so you do that cycle d times, then you can collapse it down. So intuitively, that's the way to think about the orbifold. It's just the same as the disk, but it has this additional property that a path that goes d times around the disk can be collapsed, or 2d, and so on, any multiple of d. But if it goes around once, you can't collapse it. So if we call that pi to the d is E in the fundamental group. So it's known as a cone point of degree d. So we can consider the braid group of such an orbifold in the same way as we considered the braid group for a disk or just the complex plane in Francesca's talk. There's not really much difference there. So if we take Zn of OD, it's the corresponding braid group on n strands. And this can also be defined as a fundamental group of n-tuples in OD. But it's actually probably more helpful to talk about the diagrams as Francesca did. So we can visualize elements in the following way. Okay, and this is perhaps where I should have, having this head slide is an advantage, for sure. So I'm going to draw, so 2 copies of our orbifold, which is just the disk with this point in the middle. So this is actually the space we're interested in, cross 0, 1. And it will have this special point 0, which for convenience I will move over to the left a bit because it will be in the middle. And that point 0, we will have 0, a point at every level. And let's suppose we had n is 3, so we've got 3 points, 3 strands in the braid. And then what is a strand? It's something like a timeline. So you can think of it as a particle that's starting at the top and ending at the bottom at one of the 3 corresponding points, which might not be the same. Okay, in this example, this one is the same. So it goes around the pole. So we think of this as a pole, this image of the cone point as its timeline goes down. And then we get this braid here, this strand. And then if we look at the path for this one, it could be doing something like that. And then the path for this one might pass behind it. So that would be a braid on 3 strands for this orbifold. And as Francesca mentioned, if it cycled d times around the pole, it could be pulled through. So you can imagine them sort of quite geometrically, but you just have to have that additional point that if a braid goes d times around the pole, you can pull it through. So it's quite hard to actually make that in reality. Quite maybe luckily we don't have any cone points in our space, but it's easy to imagine that kind of thing could be there. So apart from that, they are behaving pretty much like the usual braids. And I mean, what does it mean that it's a timeline and it can't turn around and go back? It must keep moving forwards. So time never reverses. So let's write BDDN for the braid group of GDDN. So yes, I shouldn't confuse things. This is now, we've now just defined the braid group on the disk. And what we're interested in is trying to describe this braid group here. So we've got the braid group of a reflection group, and then we've got the braid group of a surface or an orbifold. Okay, so the theorem, first theorem I'd like to mention is there is an embedding of the braid group of the reflection group, complex reflection group, braid group, into this braid group of the orbifold. And the image is a subgroup of index D. So it's not quite the same. In Francesca's case, we saw that it was actually an isomorphism here. But in this situation, in general, unless D is 1, when it is an isomorphism, you get a subgroup of index D. That's essentially because you never get braids which, let's think, no, okay, wait. So, yeah, I'm going to try and say that. Okay, so there's an embedding here into ZNAD, a subgroup. The image is a subgroup of index D. But I should say, so firstly, I mean, we're motivated a lot by a paper of Alcock. So Alcock looked at the case D equals 2, which is Dm. And there's also independent work of Flechsig. So also proving this result. And in fact, this is quite nice. It considers other groups as well, other complex reflection groups. And the basic idea, there's actually an important paper by Broué-Malle-Rouquier, who really define these braid groups of complex reflection groups very carefully and analyze them and in fact give presentations. So I give one presentation for each one. So you have we use that quite intensely in this in our work. Okay, so as Francesca said, an arc in the surface determines a braid, and the same thing's happening here. So an arc in OD oh yeah, I should say we're very thankful. We had some very useful discussions like earlier on in the project with Paul Martin in Leeds as well, which set us off in a very good direction. So so an arc in OD determines a braid. So if we had, I'm sort of doing this the other way around actually. Okay, but perhaps we should do it this way around, right? So, okay, so we have 0, we have the point 0, and then suppose we had 2 vertices, and then we had some arc between them, which I'm drawing blue, and then what we can, yes. So first we start with the arc. We start with the blue arc between 2 vertices. So those vertices are meant to be like these vertices here in OD. So this is inside the disk. So then we draw a cycle around the arc. So this is meant to represent what happens this point here on the right. Oh yes, okay, the star. I don't want it to be star. Right, point 2 follows the arrow above the arc, and point 1 follows the arrow below the arc. So as you look from above, this is what you would see if you think of them as particles in the timeline, that's actually what you'd see them doing. Or in other words, the corresponding braid would look like this. So okay, we've still got our hole there. Okay, I won't draw the rest of the AD, but you get the idea. An arc determines a braid in a nice way. Okay, so we'd like to get a triangulation picture as we did for the real case. So add n-1 marked points to AD along the boundary. So it's very similar, but we also regard the cone point as a marked point. So we get n marked points in general. So we get what we could call ADN, a marked orbifold. Essentially, it's a polygon with this cone point in the middle. And then we need a notion from cluster theory, and it was introduced by Fomin, Shapiro, and Thurston, which is a sort of generalization of triangulation. So a tagged arc in ODN. So it's just an arc alpha. So what properties does it have? Firstly, it joins 2 distinct marked points. So it could join 2 points on the boundary or a point on the boundary to the cone point. And it can't just be a boundary arc. So it can't just join 2 adjacent boundary marked points and be pullable to the side, isotopic to a path along the boundary. So alpha is not isotopic to a boundary arc. Between marked points, adjacent marked points. So we might have 2 adjacent marked points and we might have this. Okay, perhaps I'll draw it in blue. Okay, so that's not allowed. But if you did this, if you went round the cone point, that would be okay. Okay, so it's only if it's isotopic. Here you couldn't pull it through, so you're not. Again, if it went d times round, again, that would be disallowed because you could still pull it through. So here, I guess I'm saying if d is greater than 1. Okay, so the paths are up to isotopy, which just means you can pull them around. And you can tag the paths or not. near O. So if it's not incident with O, then there's no tag. But so in this case, there would be two versions of this arc here. Okay, so that arc could either exist with or without a tag at the origin. Okay, so mod alpha means the untagged version, so remove the tag if there is one. And then we need to talk about triangulations. So two tagged arcs, alpha and beta, are compatible, or you could just think of it as non-crossing. So this means that their untagged versions do not cross. If their untagged versions are distinct and alpha and beta are incident with O, so both incident with the cone point, they must be tagged in the same way at O. So in other words, this situation where one is tagged and one is not compatible. And if they were both tagged, it would be okay. So then you get a notion of a tagged triangulation. So yeah, somehow this tagging is taking into account the fact that you've got a different kind of point at the origin. So a tagged triangulation is a maximal collection of tagged arcs. Okay, and then as Francesca was talking about, we need a way to get braids out of this triangulation. So it's some kind of generalized triangulation, and then if T is a tagged triangulation, we have the braid graph of T. So it's the geometric dual of T in ODN. So what is this geometric dual? So it's just the same as if you've got a graph embedded in the plane, you have a geometric dual. It's the same idea. So the vertices correspond to connected components of the complement, so that the triangulation will divide the disk up into regions. And then if two of those connected components share an edge, you draw an edge in the geometric dual between the corresponding vertices. So whenever C and C prime share an edge of T, there is an edge VC to VC prime. And they might share more than one edge, and then we get multiple edges in the graph. So it's best illustrated by an example. So here's our tagged triangulation. These two arcs are compatible, even though they're tagged differently, because their underlying untagged versions are the same. So then they're allowed to be tagged differently. And then suppose we had some more arcs here. So we've got a few boundary points. We've just got 3 boundary points. And that is a maximal collection of compatible arcs. Then in the geometric dual, we put a vertex in each connected component. So we just get 4 vertices like that. And then these two are, the regions here are incident. They have a common edge in the triangulation. This one here. Yes, notability isn't quite so good at, but this edge here is common to both regions. And so we can draw an edge in the dual graph between them. So it's just a dual graph. And then similarly here. But then these 2 regions actually have 2 edges in common, the tagged and the untagged one. So we actually get this graph here. So it has four vertices and a double edge. And this is actually an example for GDD4. We've taken n is 4, and you see we've got 4 marked points in total in the orbifold there. So we can state the result. So we start with some tagged triangulation. And then we have n braids corresponding to the edges of the dual graph. They generate BDDN. So they generate this braid group. And we also have an explicit presentation of BDDN on these generators. And this coincides with the existing one of Broué-Malle-Rouquier. So I'd like to give a little flavor of how that works. So in fact, you don't have to worry too much about the triangulation. You can just say, well, we've got some kind of embedded graph on 4 vertices in the disk here. So in this case, we've got this blue graph here. So the triangulation is a way to get certain kinds of embedded graph in the disk. So, and I think at this point I will go to, right, I won't try to write all of these out. So just give you a flavor. I've drawn these in black, but that's okay. So these were blue on the previous. So okay, so we might have 2 edges in this dual graph. So these are edges in gamma t. So they might just be far apart. So like Francesca's far apart transpositions, and then the corresponding generators commute. And they might have a vertex in common. And then, as in Francesca's case, you get this longer relation, sometimes called the braid relation. And what might also happen, that also happened in Francesca's case, you might get a cycle relation. So you might have 3 edges in this braid graph making a triangle. So then we're braiding along these edges. That's the way to think about it. So you might braid along one edge and then the next edge and the next one. a bit like braiding hair, I think. So, so you get a cycle relation. So that again, that's not anything to do with the orbifold. But then you start to get new relations. So here star is this cone point in the orbifold. So if you braid along each side of it, you can see where this relation is coming from, because if you go around d times, it's the identity. So if you braid along each side d times, it doesn't matter which order you do it. And the next one says that if you, it's a little bit similar. If you keep braiding around and around the cone point, you have to do enough braid. If you do enough braids, it doesn't matter where you start. So if you do something at the right length, then you start with S1 and you do dr-1 terms where r is a number in the cycle. You do dr-1 of those. It's the same as if you start at S2 and do the braiding there. And then there are some other situations which can arise, and there are some relations there. But again, the relations are fairly simple. Just two more cases there that could essentially, this is based on this, what these pictures are. This is what could happen at the cone point. It could be with triangulated like this, and then the black arcs are the braids. So there's a relationship between these four braids in this situation. So we're running out of time, but there is a similar picture for a presentation of the reflection group as a quotient. You just have to add SI squared as the identity. And you can explicitly describe which reflections you get. So it's a similar group level. And I perhaps could also draw, the quiver can also be drawn from the diagram. And it's appearing in red there. And the quiver is actually what appears in Broué-Malle-Rouquier's paper when they're describing their presentations. So it gives some kind of sort of geometric explanation of their diagrams. Okay, I'll stop there. Thank you very much.
Thank you very much, Bethany, and thank you both for your talks and presentations. I think we have a few minutes for questions, so let me check first with the audience. There are no questions in the Q&A. I wonder if there is anything in the chat. Let's check. There is a lot of thank yous, but not questions. So is there any question from the audience or any comment? You are more than welcome to ask the question by unmuting. Okay, if not, perhaps I can ask a question to you both. So more for the benefit of our early career researchers. So what you have given us a variety of presentations. What do you get? How do you select your presentations? So you in both talks we saw different presentations. So why you look for more than one presentation? What a different presentation brings to the understanding? What guides you otherwise in looking for presentations?
Yeah, that's a nice question. I mean, it's something we also think about. So I mean, it seems that Coxeter, it goes back to the Coxeter presentations of reflection groups. And Coxeter found these very efficient presentations in the early part of the 20th century. And they have very beautiful properties. And I think after that, people have always used those presentations. They've been a focus on this presentation. And that has been incredibly successful. And there's a lot of work been done on those presentations. And if you're thinking about reduced expressions for elements and things like this, so the combinatorics associated is really interesting. But I sort of feel that there's been a lot of focus on those presentations, and at the expense of other possible ways to describe these groups. So it could be that we're missing some understanding of these groups by focusing only on one presentation of them.
Yes, thank you. I mean, we often sometimes lose track of what really motivates us. So I really think it's fascinating to look for different presentations, because they might bring in different properties, and they might indeed enrich our understanding. So along the same line, how do you choose, this is a new project for you both. How do you choose, the project you want to work on? What are the criteria that you use to select among many ideas that you might have, or a variety of issues that you see arising from your previous research, or recent research? How do you then decide, okay, that's really the one I want to select as a new project? Again, thinking to the audience, which is made of more junior mathematicians, perhaps if you can say something. And I would like to ask Francesca first, and then perhaps Bethany.
I guess this is I guess it depends. You can have different motivations for different reasons. I think, for example, for this one, we were just very intrigued by this sort of presentations and so on that link very different objects in different parts of mathematics. And we were very intrigued by looking for more connections and looking for more understanding of this. And I have to say, at the beginning of this project, I really didn't know anything about any of this. So it was really great to have Bethany, who, as I cited in my talk, had already a lot of previous work on this to teach me some of this. And then we started looking at this. And yeah, I guess for us in this project was really trying to link different things that are not obviously connected by using these nice combinatorics and these different tools. But yeah, maybe Bethany wants to add something as well.
I should say, I think you've been teaching me more later in the project. So I think it's curiosity as well. It's like, okay, so maybe you understand the real case first, and then you think, well, okay, well, there are these other groups out there, maybe something still works. And I think another thing I'd say to early career researchers, I think, don't feel like, oh, someone must have done that. It's very easy to start thinking, oh, that must have all been worked out. But if you found something and you're finding it interesting, then go for it, because it may not have been the case. What might be obvious to you might not be obvious to someone else. And I think take the point of view, if you've got something that seems like something reasonable, but there probably will be some mathematics there, will be some great mathematics there. Mathematics should never be ignored. You've got some idea there, you should just follow it.
Well, thank you very much, both Bethany and Francesca. I think the way you moved from real to complex, for example, was really, really fascinating. And the curiosity that comes from that move was really evident. And I guess the last advice you gave was really, really precious. So fantastic. We are running out of time, and I think the time is over, but it was really a pleasure to host you both. I think it was a fantastic double act and a fantastic 2024 Mary Cartwright Lecture. So on behalf of the LMS, thank you so much. And I hope to see you soon, perhaps in person in the near future. But thank you. Thank you very much again for your time today.
Thank you. It was great. Thank you very much for this opportunity.
Yes, thank you. It's been a delight.